Okay, we're gonna go over some questions in mechanics, and the first one that I wanted to go over in this video was one in which it said that there was this vector that they give us coming from the origin. Actually, that angle would be this one a bit more accurately, and this was O here, and that was X, and that was Y, and they gave us that the vector was vector F, and they told us that vector F had a magnitude of 4 newtons. So vector F has a magnitude of 4 newtons, and the angle between F and OX was 30 degrees. So they give us this here, and they ask us to calculate the components along the X and the Y axis. The component of a vector, what it means when they ask that is how much of this vector, which is going in that direction, how much of that is going to have an effect in this direction here. That would be the OX component of F, and if you imagine there's a particle here, then if this force is acting on the particle, then the amount of force that would actually try to move it in this direction, ignoring the up and down motion, that's what the component of F in the X direction means. So we can write that the component of F in the X direction is equal to this shadow here. Basically, if you were shining a light from here, then the light would come over here, and then the vector would block the light, and from here onwards this would be the shadow. So you can do a 90 degrees triangle here, making sure the force that you're going to split up in two is your hypotenuse, and the Fx component would be the cos of that angle times the hypotenuse, because this is the adjacent and the hypotenuse, and the AH from K is the cos part of the triangle. So then we could say that Fx is equal to the full vector F times the cos of the angle 30, which in this case we're going to write the general theta there, and then here we can write the specific case where F is 4 times cos 30. So that would be our f of x, F in the direction of X. And if I do that in the calculator, 4 cos 30 comes out to 3.46 newtons. 3.46 newtons to 3 significant figures, and so that's this component here. Of that vector, and the other one would be how much of that force is going up. So that would be the same as this, since there are two sides of the same rectangle, right? And imagine the rectangle, draw it in white. The full rectangle would look like that. Actually, that should be in green because it's the same component as this one down here, right? The same as this one down here, and the components are this one and that green one there, and these are just the sides of the same rectangle. So in order to find the height here, or the how much of this vector F is going up, we need to do the opposite and the hypotenuse trigonometric function, so that's the opposite, and hypotenuse would be sine. And since we're doing it in yellow, this would be here Fy, which is the same as this one here, and here we would have Fx, which we just calculated, so Fy would then be F sine theta, which is equal to 4 sine of 30, and that is, well, sine of 30 is a half, so that would be 2 newtons. So this is how much force is going in the up direction, and this one is how much force is going along. And these are called the components of the perpendicular components of that force. And what that means is that you could substitute that force which they give you there in the question, which is this one, with a magnitude of 4 and an angle of 30. You could substitute this guy completely and basically take this force away, acting on this particle that's here. This would have exactly the same effect on the particle that's here and being pulled in direction as if you had the particle here and you had one force going in this direction. So you can imagine nearly 2 people doing this at the same time, one of them with 3.46 newtons and the other one doing also pushing it or pulling it upwards with 2 newtons. These two forces acting simultaneously on this object here would have the same effect as this single force there. So that's what components mean. You find 2 vectors which represent this one here, and they would have exactly the same effect. Why is this useful? Because when you have, and we'll do this in a few examples, in 2 or 3 videos from now, we'll do an example of this, where we have several forces like this one, not only one. We have one force like that, maybe that would be like this one at 30 degrees, and then maybe we could have another force there acting like that at this angle, and then maybe another one here going straight down, something like that. And then if we were asked how to add these 3, that would be quite a difficult thing to do with a polygon, where you start adding them and you want to find the angles, and using trigonometry and the sine rule and the cosine rule and all of that, it would be quite hard. So an easier way to do it is by splitting these into components. So you literally split this one in 2, one of them would go up and the other one would go right. You then split this one in 2, one of them would go like that and the other one would go like that. So you need to find 2 vectors that add up to that one. And this one you don't have to split it because it's going already straight down. So now that you have these at right angles to each other, you can combine them. You can combine you can now add them, and they add as normal vectors. So you have this one here going up, and that one going up, and this one going down. So you add these 3 vectors and you would have a resultant. Let's say that the resultant is up by this much, because there's 2 going up here and 1 going down. Probably end up with an up overall resultant. And then you'd have to do the same thing with the ones that are going sideways. So then the ones that are going sideways are this one and that one. So these 2 you then combine, and it looks like the right one is bigger than the left one, so you'd end up with probably something like that to the right. And then you would have the 2 final components, which represent all of these together, would just be represented by those 2 at the end, and they would have the same effect as all of those combined, these 2. And the question could then say, alright, so now find the final resultant. And then you'd have to add these 2 by using normal Pythagoras, where this is the same size as this one, that one, so you do this squared plus that squared equals this squared, and you get your resultant. And then if you want to find the angle, then you do tan theta, because it's opposite divided by adjacent. So you've got your opposite here and your adjacent there, and which are the two magnitudes of the two vectors you just found out, and tan theta would be the opposite divided by the adjacent, and you could then get theta by doing the inverse tan of that. Okay, so that's a little sort of talk about vectors in general, or the kinds of things that you can be asked for here. So just as a recap, here we were being told we were given one single vector, which was f, and we were asked to chop it up into two components that make it up. So two components in the OX and the OY. There's no reason why you have to choose those directions, but it's normally better if you choose them well, it's definitely better to choose them at right angles to each other. But that doesn't mean necessarily that they have to be along the OX and along the OY. Sometimes we'll see a situation a little bit later where sometimes it's better not to choose them horizontally and vertically like this. It's a little bit better sometimes to choose them at an angle. So maybe you choose them at this angle, right angles, but maybe at that angle instead. So here we were given one vector, we were asked to chop it up in split it into the components along the X and the Y direction. And that's fine. And then here I was making the point that the meaning of that is that these two vectors have exactly the same effect as this one here, as the full vector. That's what we've done in chopping it up. And that sometimes the usefulness of doing this, of being able to split it up, is that sometimes you have a whole mess of vectors, like we had here, the red, the blue, and the white one, even though it's not very visible. Now you had a vector like that, and another one here, and another one there. You could have all sorts of vectors, and the way to add them up in an easiest way, instead of trying to go making triangles and adding them heads to tail and all of that, you can just add the components going in this plane, and the components going in that plane. You could add those two individually and you end up with one vector like that and one vector like that, or in any direction, but you end up with two vectors, and these two you can combine them, as I was saying here, in the end to find out a final resultant force that is equivalent to all of these together. That would be what we get at the end. But here, the question that we did, we weren't being asked for that, to find any resultant. We were just be given the one vector only, just so that we practice, and asked to chop it up into two components. So that was it. That would be the answer. One of them components would be X and the other one is Y. So hopefully that makes sense, and we'll do a few more examples in the following videos. And one more thing I wanted to mention was that it doesn't really matter what order you add vectors in. You can add a vector like that and a vector like that. You can add them in any order, right? So you could go, for example, first right and then up, and then you have this resultant, or you could go first up and then to the right, and you would have that resultant, right? But this resultant here and that resultant there are exactly the same resultant, because they are two sides of the same rectangle. So I can now add these two here if you want, and you can see that they're sides of the same rectangle, and then really what we're calculating is the diagonal. And this is when we have at 90 degrees the forces, then it's a rectangle. Let me see, I'm being a bit lazy, let me explain it a bit better. You could have two vectors that are this and that, those two vectors, and you can add them in either direction. Means you can you probably understood it from what I just said, but you could either add them let's paint them one like that and one like that. You can add this one like that first, and then this one here, and then your resultant would be this. Or you could do it the other way around, that you could have first the blue one and then the red one, and your resultant, which is the green, would still be the same. So you've got the two here which are the same. So hopefully that helps too, and let's go to the next video.